So I'm
Good
David.
call.
I am heading up engineering education at Timescale. And so welcome. Also, Miranda is here with me as usual today. If you want to introduce yourself, Miranda.
Yeah, what's up, everyone? My name is Miranda, as David said, and it's written on the screen, I guess. So, yes, my name is Miranda. um, I am a developer advocate here at Timescale, and so I kind of come more from a theoretical mathematics background, and more like just know the applied side of databases. So I've been really enjoying really learning with you all from David, kind of more the conceptual side of databases, and learning like more in depth, or I guess we haven't quite gotten there yet, but learning more about how Timescale does creates some of the functionality and features that we have. So
Yep.
yeah.
And Miranda is going to be acting as sort of audience liaison and asking questions that come up and helping me manage those. Let's get started. Um,
What?
with another bit off topic. Does anyone? This is our sort of pre-show question. Does anyone recognize this?
I recognize the next slide.
Logo, and you recognize the next slide. I thought you might. Okay, does anyone recognize either of these logos here?
I'll wait.
See if anyone in the chat wants to
Pro, I
reply
feel like
here.
it definitely feels like an old, like some circa, 2000 icon that I can't put a finger on exactly what it is. Anyone in the chat? Any guesses? What about the next one? Does anyone know before I spoil it? Come on. Come
Okay,
on. My
we got it.
statistics
We'll,
friends,
we'll move
MATLAB.
on. This isn't that interesting. It's MATLAB. The other one is FileMaker Pro. And I was going to
FileMaker
reminisce
Pro.
about when I actually started working with databases back in like 2014-ish. I actually also don't come from like a computer science or other sort of background. I like was in engineering and was working with at a battery company, and like my coding background, I'd taken some engineering classes, like coding for engineers essentially in college. So I'd done some C and C++, some Fortran, and some MATLAB. And we were working with MATLAB and FileMaker Pro as our like databasing tool, which was really bad. And trying to
Oof,
get MATLAB to talk to FileMaker Pro was,
that
let me tell
sounds
you.
like a disaster.
I eventually got it to talk to Postgres. I also got it to talk to an Oracle database that I was working with. Somewhere in the middle, there was a bit of a time with MySQL. Anyway, one of the things that I really liked about MATLAB, and that I really liked working with MATLAB, was that like the integrated debugger in MATLAB is really good, and it would allow you to like step through programs and highlight what parts of data structures had changed when you were doing that, which I found was like really helpful for figuring out what was actually going on or going wrong in certain cases. And I think that it like that way of thinking about data structures, what's changing, et cetera, something that I've always enjoyed doing in terms of coding. And it's actually one of the things that I like about Postgres and Timescale is that a lot of what they're doing in terms internally and managing themselves is actually represented in the database. Those are the catalogs. And so you'll see, and that's what we're going to be discussing today. I just want to, so that this is lesson 6, our 7th lesson because we started from 0. Uh, and as if you're just joining us here, like this is something that we're releasing publicly, but is really meant as an educational tool for folks who are joining Timescale to learn a bit more about the database. It's also, but we figure it might well be useful for users who want to get a more advanced sort of picture of things. So one of the disclaimers that I want to have before we go into this is like, you don't need to understand any of the stuff that we're going into today in order to use Timescale. It might be helpful. It might help you use it better, but a lot of the stuff that we're talking about here is like stuff that we have explicitly like done to like hidden almost, like made so that it just works and you don't have to understand it yourself. So it might help you understand what we're doing in the background, which might be useful for certain types of tuning and other sorts of stuff, but like it's not something you need to understand. Um, so um, one of the big things there. See, this is where I skip over slides because it's basically, I just what I said. One of the things that we're going to be talking about there is the difference between partition management is DDL, which is what like normal declarative partitioning in Postgres does, versus what we're doing, which is what's happening during DML. And we're going to explore this by exploring the catalog. So we're going to hop over to. I've got two different sort of clients here, PSQL and Postico, which is a Mac Postgres client that I like. I have a few different things, some of which are already done and some of which are not yet.
Question.
Yes.
Is there any way to increase the size of the font for the left side?
For this?
Yeah. It's
No.
just a little hard to see. Okay.
Not that I know of anyway. I haven't
Wah,
figured out
wah.
how to do it, unfortunately. I can get it to like increase the font over here, but not for these things as far as I know.
That's cool.
I could
Just
try,
was
but
curious.
anyway,
Just was
we're gonna look over here for the most way. I'm gonna, and then I'll set it up again. But eventually we're gonna do that. But for now, we can see is that I've got so I was actually running through the new tutorial that you made, Miranda, or helped
boy.
make. And it's lovely. I really like this new one. I did this a while ago, so some of the dates are it's still out of date. I haven't downloaded the new stuff. Sorry. Um, but you'll get the idea. And so we have a table called company and a table called stocks real time, which is basically just if you go to our getting started tutorial, that's sort of what we got going on right now. So you'll be able to go and see that. You can download some of this data yourself if you want to look at it. We also you'll see that and this is basically the commands that I ran, right? So we created the table. We also turned it into a hypertable, and I inserted the data as well as creating the index. Now we can see that this is actually a table, right? We can see we can run one of our functions that helps describe things. We can see the size of our chunks. Excuse me. Here, so and you'll see various places where those chunks exist and how big they are, right? So they're reasonably sized chunks. It's a useful thing here. Just to get an idea, yes, there's data here. I've already inserted it. We're going to use that as a starting point. So if we are looking to explore this a little bit more, and by the way, I'd really love your questions on this. I'm going to be exploring it and sort of going through. This is definitely something where I want to be guided by your input.
Yeah.
So if there are things that come up that are confusing, whatever's going on, please let me know. One of the reasons that I decided to do this lesson was that we'd had a number of people who were like, oh, like who really found this exploration of the catalog helpful. I've done it sort of a couple times just for different people who were like, oh, okay, that really helps me understand some of what's going on here. So I wanted to do some of that for that reason. But also, like, it can be a little bit confusing, and you should stop me if there's anything that's not quite making sense.
Yeah.
So
Definitely ask questions. I see that there are a few of you watching, so
yeah,
feel comfortable to ask questions because we love them.
yes. So when I'm going through here, like I can find some information out about these tables. I could go into the Postgres catalog to look at like all the different attributes and other sorts of stuff. I could look at the all of the columns and how the table's made up. And that's what really something like this is doing, or even PSQL is doing. When it's telling me what's in a table or something like that, it's using the catalog. Um, uh, uh, so it's using the catalog to figure that out. Now it's using the PG catalog. It's also maybe using the information schema. You'll notice that if I show our and hi Fahad, and we have, I think you're asking whether we've covered installing TimescaleDB. I don't think we've covered it in this series in particular. This is really meant as a more theoretical overview. However, our docs definitely cover that. And I think we have some videos that do that as well. There are various ways to do that depending on your system. So I would recommend going to the docs for that. So the thing that I wanted to show here, so if I show my schemas, right, we can see some of the schemas that exist. Now, we have our public schema, that's where our tables live. We also have some of the TimescaleDB schemas. You'll see that there's this TimescaleDB information schema. So that's like the information schema in Postgres. It has some views on top of the catalog that help us understand some things. And there's also the _TimescaleDB catalog schema. And so I'm just going to put, so let's take a quick look at what's in there. We can see /d. Oh, that was bad. Whoops. Oh boy. Too much. Let's /dt so that we just see what tables there are in the catalog. We're not going to get all the other information. So this tells us what relations are in the TimescaleDB catalog. And if I do the same thing for the TimescaleDB information, we'll see some views. So if that's /dt is described tables, /dv is described views. I forgot how to do this before. We'll get to it in a second, actually. So like one of the things that we might want to know, we had some like chunk detailed size. We ran that function to get some information on that, but we might want to know the chunks that exist and some information about them. So if I select, and actually what I'm going to do just so that this is a little bit easier, I'm going to set my search path so that TimescaleDB catalog and TimescaleDB information are in my search path, so that when I do this, I don't have to schema qualify everything. So I'm going to do that. And I'll just say select star chunks. And we'll see, because I actually only have one hypertable right now. Oh, man. I wish I could make this big enough that you could actually just do that, but apparently I can't. So we can see the results here, and that for instance, it has the range start and range end of where the tables start and end. I wish that I could make this big enough so that it could actually fit on the page, but it's not. I guess if I made my text smaller, I could do that, maybe. Can you still see it, or is it too tiny? Aha! Better? Worse?
It's a little tiny.
Okay. Worse. That's tough. Fine. Okay, so maybe that's fine. We'll just, hey, that's what happens. Okay, so then, so let's look at what I can also just do the other view, right? So I could do extended display, and we could look at it this way. Maybe that's better in this case anyway. So we can see, right, that we have the hypertable name and the chunk schema and chunk name. And we also, you'll notice that we're referring to everything in here with the hypertable schema, hypertable name. So like this is giving us the range start and range end in times. That's nice. You'll see that we have 7-day chunks, right? We notice that it's not compressed. And there's various other things that are useful here. So that's some of what's going on here, is that we can see these chunks exist. And I'm going to turn expanded display off for now. So that's a useful thing that we can see there, is just when are the range start and range end. And in fact, why don't I just select. Now, if I look at chunk, which is in PG catalog, or in TimescaleDB catalog, chunk, right, you'll see that that's a little bit different. So if I look in the catalog, in just the catalog, all it has, it seems, is an ID, and some schema and table names. It has the Hypertable that it's referring to. It has a compressed chunk ID, but I don't see any like time ranges for those chunks in this catalog. So one of the things that we might want to try to understand as we're doing this and take a look at as we're going through this is, well, how do we actually get that information? And the answer is that it goes through a table called dimension and dimension slices, and we're going to look at how that works. Because I think that that's an important bit of some of the underlying infrastructure that might be useful here. So in order to figure that out, one of the things that I might be able to do if I want to know where that is coming from, like how do I figure that out from just like looking at the catalog? Well, one thing I can do is I can understand what is in the underlying view, right? So if I know that my chunks view in TimescaleDB catalog, right, or TimescaleDB information, this is the product.
Honestly, like whenever I
Right.
first was shown this, it helps so much in understanding chunks, like going into the catalog and stuff. It's awesome.
Yeah. So we have this here. So what is this view actually doing? And we can use the show view command to actually understand what is going on in that view. So /sv is going to be that command. I forgot what that was, so don't worry if you don't know it. I thought that it was /dv plus or something like that, like dt plus, but it's not. It's /sv. Why? I don't know. But /dv plus does not work like it does with tables. Or /d plus and then view name. I think maybe it's just /d and view name. I could try it. Let's see. So that gives us the column information and it tells us that it's a view, but it doesn't tell us anything about how that was created. And even if I do /d plus, you'll note that it doesn't actually. Oh, it does. Hey, that didn't work last time, or I did something wrong. Okay, well, okay. So the view definition does appear here, and that's really what we were looking for. The other way we can do it is /sv, right, and that gives us a view definition. But let's do /d plus chunks. That's even easier. And you don't have to remember as many things. Okay, so we can see. So we're trying to figure out which column goes to which. So let's first off take a look at this just to see how we're trying to figure this out because it's a little bit hard to figure out. So we have chunk dimension num. That's not the one that we're looking for. Primary dimension type. Okay, those are maybe useful. How do we get the other stuff though, right? So you look for all the ases. So if we see range start, end as range start, end as range end, right? So these are case statements. And this is basically because we have to, there's various different types that we have to deal with, and we're casting things in order to figure that out. But the main thing here is that we get the range start and range end, and we can see what it's actually doing to calculate this. So it's using the dim table, and it's using this dims1 table in order to calculate the range end and range start. So dims1 is this dimension slice table, and dim is dimension. And we're also looking, you can see at this chunk constraint table, like that's how we're actually getting to. So if I trace this back, you can see that this dimension slice, my join to dimension slice here, is going through this chunk constraint table. And the as well as my my dim table is going to my original chunk table, which is the one that we were looking at before. So when I look at these tables, or when I select from these tables, chunk, right? So from so this is not schema qualified because I think because of my search path, but I'm not 100% sure. But you'll see that these, so like the chunk constraint table, dimension slice table, all of those are coming from the TimescaleDB catalog. And if I reset search path, I wonder if it does that. Okay, so now you can see exactly the schema qualified, the full schema qualified version of this, right? So you'll see that these joins then are happening to these things that are in the catalog. So I can look at each of these tables in turn, and we can see each of them. So we already started with the chunk table. Right, so we saw that. We see this. There's this Hypertable table, right? And we see that we're going back here. So we see this Hypertable ID. We need to join to the Hypertable table. And we should just see one Hypertable here, right? So we see all of the information about the Hypertable there, right? Like it tells us, hey, this is the stocks real time and timescale underscore hypertable underscore hyper 5. Where is it actually? This is a chunk sizing schema. That's for stuff that actually is deprecated now for automatic chunk sizing that didn't quite work correctly. But so that's how we can sort of explore this. But but what we learned is that we're going through this chunk constraint. So if I look at this chunk constraint schema. Doesn't give me that much information, right? It just has some constraint names, right? Like, that's not really what I was expecting. I was expecting the constraint to like say something like, "Hey, the constraint, like this chunk has to include data from this time to this time," or something like that. But it just gives me a constraint ID. Now, why is that? Well, you'll note that in order to get these things, we really have to go through these dimension and dimension slice tables, and that's where I'm going to keep going in order to figure out what these constraints are. You'll see that in here we're referring to the dimension slice ID, so we're eventually going to need to get to the dimension slice table. And so if I do that, if I select star from the dimension slice or dimension table, so the dimension table is pretty simple. Right, there's just one entry because I have one hypertable and it has one dimension, which is time. You'll note that so the column name is time, the column type is timestamp with time zone, right? It tells us our hypertable ID and the dimension ID. It also says that this is aligned. It says aligned is true. Now, what does that mean? That's something we'll get to in the future. In general, aligned dimensions are often what we also call open dimensions. And we'll see what exactly that means as we go forward with this demo.
And so
I
was just about
the
to
interval
ask.
length.
Yeah.
What were you going to ask?
Oh no, I was just going to ask, like, what is? I mean, obviously the interval length. Is it in milliseconds? What is that?
Yeah.
What is the
Okay.
measure of time?
So let's look at. That's a great question. So let's describe this table so we can see what its column types are. Say so. Right. So if we describe this table, we can see that the num slices is a small int. We'll get into that later. But we saw the interval length, right? That's a big int. Now, so the interval length here is describing the amount of time that's between things. So the timestamp type or timestamp TZ type in Postgres is represented internally as a big int. And in fact, all of our tables, all of our slices, and actually if we look at maybe it's time to look at the dimension slice table, right? So if we look at dimension slice, see that our range start and range end also big ints. And if I could also do that, right, right, you'll see that those are big ints. All of these are big ints. So the key thing there is that our range start and range end are big ints, and everything that we do in terms of our constraints is done in that internal big int type. And always the constraints on a chunk are always translatable into that big int type. So even if we do space dimensions, it's going to be some slice of the hashed space of a big integer or a smaller integer, depending on what you're doing, in which case it'll take over some portion of the big int space as well, but that's fine. So we can look, and we'll look at that in a second. But so we convert it internally into its internal representation, which is an integer. And we always use that because that allows us to then have one schema, whether we have an integer, whether we have a timestamp, whether we have a date. So all of the different types of partitioning columns that we support can be interconverted with integers. And everything is based on integers. And the way that we could interconvert things like text, which we allow for space partitions, is by using a hash function.
And is this UTC conversion to the big int?
No. It is Postgres's own.
Oh.
So sorry. Is it UTC? If it's a timestamp TZ, then it is UTC.
Okay.
If it is a timestamp, then it is not. It is at local time.
Okay.
Right. It is represented at local time. So that's a different question, is like whether it's a timestamp or a timestamp TZ will depend on which way it's converted. It is also not the same as Unix time, which is maybe what which was what I thought you were asking at first.
Okay.
It is actually a Postgres specific internal representation of time that happens to start at, I think, 1990. I don't remember exactly what the 0 point is. It has a slightly different 0 point, I think, than Unix time.
The traditional. Okay. I wasn't sure what it was
called.
Unix time. Okay.
I don't know.
Interesting. I did not know that.
But it is, and whatever. Like, yeah. So,
I mean, I guess if it works.
Yeah. So. And the decision of using a big integer means that Postgres can represent some, like, essentially it has down to microsecond precision. So a timestamp type in Postgres has down to microsecond precision, and it has some range of times that it can represent, determined by where that 0 is set. Right. And if you need a wider range of times, well, there are various things you could do, including, for instance, storing an interval as an offset and saying, like, all of my times are offset by this interval, and you just have to, like, figure out how to, there are different ways that you can think about doing that, but whatever. Anyway, most things in the real world, certainly in our use case, like, you do not need to be going back in time further than it goes, nor forward in time further than it goes. If you are cool, you're probably a geologist or something. Like, great, have fun. Don't know what to tell you. Maybe use an integer with whatever. Like, you probably, in that case, you probably don't need microsecond precision. So maybe, like, use a different format. Anyway, we will leave that aside. And okay, so we have these dimensions and dimension slices, and one of the things that I want to show you is exactly how these are. So we see that this range here. We note that when we do the select from the TimescaleDB information.chunks, right? So if we select, right, we can see that this range start is 2022-03-31, and the range end is 22-04-07. So that's a 7-day thing. That's the default that we do. And in fact, what I want to do next is just create the same hypertable, and we're going to insert some data so you can see exactly how this stuff changes as we do inserts. So if I've already created this table, I'm just going to create a copy of it, essentially, right? I had this drop just in case I had it. So we're going to create this stocks real time new, right? And by the way, I added here just so we could see. I added a check constraint as well, which is something that I know is true for all this data, right? That the symbol is equal to the uppercase version of that same thing, right? So it's just, I wanted to make sure that it was an uppercase. Cool. So that's my check constraint, just so we could see how that would also get represented. Okay, so we've created the table. Nothing changes until we actually create a hypertable, and we're just going to use the default. But just we'll say chunk time interval, and it's 7 days. So we'll just use the usual one, but I just wanted to make it explicit here. Okay, so we have a new hypertable 11. So if I now, first off, let's look at, we could either look at TimescaleDB information or TimescaleDB catalog. Let's do catalog.hypertable. Why? Now we have another hypertable. Cool. It has one dimension still, right? We have and it has our correct name, right? It's in public stocks real time new. So we have that new hypertable. Do I have any chunks? Anyone want to guess? No, right? All my chunks are from my other hypertable. So if I were to add a where clause, there are no chunks yet because I haven't actually inserted any data, and we create the chunks automatically when you insert the data. We do not pre-create the chunks. However, there will be a dimension. Did we ever look at dimension slice? Anyway, whatever. But there will be a dimension, right? Because we created that time dimension already, but there will be no dimension slices because, again, we have not inserted any data yet. So if I select everything from dimension slice, you'll see that everything is still for the other dimension ID, right? That's for hypertable 5. Whereas our dimension ID will be 16. Though if we had another dimension, we might have multiple dimension slices associated with the same chunk. Okay. So and also we'll see chunk constraints. If we look at that, that's also a little bit different, but let's actually like create a chunk now. So how do we create a chunk? Well, we insert some data. So I have that written up over here. Oh, I need to create this index, same as the other, but okay. So if I insert into this table, and I'm going to insert data from this day, and I'm just going to choose one symbol randomly just because that makes it a little faster to go. So I'm going to insert some data from April 4th to April 5th. So if I run that here, that inserts some data, and we'll see that all of this now has changed. So if I look at my TimescaleDB catalog.chunk, now I have this new chunk. And that chunk will also have a dimension slice associated with it, right, with my time dimension. When I look at the chunks informational view, you'll notice that this has the same range start as the other one, and that it's on March 31st. It's not on April 4th, even though I inserted data from April 4th. So some people expect that our timestamp that we insert in is going to be where we start the chunk. But we actually divide space evenly into 7-day pieces if you have a 7-day long chunk. And then we insert data, and we create a chunk that matches a slice of time that is 7 days long. And it's not necessarily starting from the point where the first point that was inserted is just a chunk of time that's 7 days long. And all the data will fall into that. So, and it's the same sort of thing like with time bucket. So like, I think that it has the same origin. So if I were to time bucket this into 7-day buckets, you should end up with that starting time or something like that. At least that used to be true, but we may have changed the default origin. I don't know exactly what's going on there. It's essentially so that we can do integer arithmetic on it. And just do integer division to get the chunk that we should be going into, right? So that makes it fast to figure out how to locate which chunk a given day belongs in. So we'll check to see, now, if I were to insert more data from the same day or that belonged in the same chunk, right? Obviously, I'm not going to create any more chunks. Now I have the chunk that belongs in. So I no longer have to create a chunk there. It already exists. So this is the sort of thing that we were talking about when I said we've taken partition creation from something that you did during the DDL phase. Like, I don't have to pre-create all of these chunks. I just have to set up the hypertable, and now it will create chunks for me. I don't have to create each one individually. And it's going to do that during the insert. Now, we had to do that with, like, there's various things that we have to do to make sure that works right. And that's what we're going to go into sort of next. So if I keep doing this, just a couple quick things before we get into like space partitions, which are even more fun. So if I keep doing this, one thing to note is that if I change my chunk size here, it'll only take effect once the next chunk starts. So if I run select set chunk time interval, and I use this, right? And I say I want it to be now 1 day instead of 7 days. Well, that's not going to take effect until my next chunk is created. So it's not like it's going to go back, and if I run this again, right, it's going to say, oh, I truncated that chunk down for you. Right? No, that chunk stays exactly the same. It still goes from March 31st. Let me see if I can just get these to appear on 2 separate lines at least. Or all the way. How about all the way over? Okay, so maybe that's a little bit better. So it goes from March 31st to April 7th, and it still does, right? I'm not changing anything about that just because I changed it to 1 day until I insert data, right? So if I insert, now I could just sort of keep copying and pasting the statement, and we'll do this, and we'll update our dates. So if I do this, I could go from 5 to 6, or hell, we'll just go straight to 7, right? So if we do that, right, that's fine. No chunks were created. Right, still the same number, still 6 chunks, still going from March 31st to April 7th. No difference there. But then once I get beyond April 7th, 7th to 8th, or even 9th, right? Now, if I run this again, you'll see that my chunks have now, like, I have more chunks now that I did that. But you have to wait until that first chunk is done. We don't ever close a chunk prematurely. We basically try to avoid modifying those constraints that are on the chunk, because that is a very expensive operation. Let's look, by the way, at the actual constraints that are on the chunk. So we can see the chunk name here.
So just curious, I have a question.
Yeah.
Then how do you, so we still see that the Hypertable 11 has that chunk 2697. When does that get broken up into days? If you keep inserting data within, so that chunk will never actually change to be an interval of 1 day.
No,
it will always.
It only happens for new chunks.
Interesting. I did not.
So you have to get past the next time. So
what if you wanted to break up? Like, is it possible to break up a chunk that's already been created, or would you have to like recreate the table and like
so usually that's not necessary, and there's like, so usually you're making chunks smaller mostly for the insert performance.
Not as much for
so
read.
like you're not really going back in time and adding, like, you actually want fewer chunks for reads to an extent. Like, you have to, that's one of the things that you have to sort of optimize, is like, you don't want too many chunks, because that can slow some reads down, though we have some good optimizations that are making some of that faster, coming in the next version, which is exciting. But there's also like
So
yeah.
on the flip side, then, if you have like lots of small chunks, say that you start off working with a smaller amount of data where it makes more sense, you're ingesting data, so it makes more sense to keep small chunks. And then as you kind of your database grows,
Hmm.
so is there I guess there's is there a way to then kind of combine those chunks for better read performance?
There
Or
isn't right now. That is something that we've talked about.
okay,
That we've talked about being able to merge chunks, or potentially split. Like there might be an operation that we could do on that eventually. For now, we've decided not. Like it's usually more effort than it's worth.
got it.
You can always copy it over to another hypertable if you really want to, but usually that's not like often people are keeping some amount of data around and they're dropping chunks anyways. So like
Okay.
it's only gonna be around for so long, all that stuff matters. I'd say like, don't make your chunks too massively huge, but also don't make them too small. Like you really don't want tiny chunks to start off with. So like, but making them 3 years long, like that seems like probably overkill. Like make them a month or two
Maybe it's
at
yearly
most, or
data. No, I'm
like
just
so
kidding.
that's why we sort of go with 7-day chunks as a
Right.
starting point. Is a reasonable size. Like you can usually figure out things for a little while if something needs to change. Like okay, like 7 days is an amount of time that isn't crazy to do that with. Um, so that's the basic gist. Let's take a quick look at so if we look at the dimension slices, you'll see that now I have my 3 dimension slices, one that is 7 days long, and then these ones that are 1 day long in big int terms, but that's not something that we necessarily need to know. My dimension table stayed the same. My chunk constraint table is interesting here. I guess it doesn't add check constraints. It only adds unique indexes. Okay, well, we'll do that another time. Anyway, the point here is that so we have our constraints that are relating to the dimension slices that we're going back into. So you'll see that these correspond here, right? So our constraint over here, our constraint number corresponds to the dimension slice ID here. So that's how those are named. And if I look at the actual definition of the hypertable of the chunk, right? So if I do um, uh, right, I can see the constraints. You can see one, I have my check constraint on symbols, right? Like that's always propagated down to the chunk as well. But I also have this check constraint that is on my dimension on time, and that it's between the 7th of April and the 8th of April. And you'll note that all of these are always inclusive on the left and exclusive on the right. Right? So we do greater than or equal to and less than. So that ensures that we get just the time that we want. So let's keep going here in our I'm going to actually drop this one. And now we're gonna make a different one, and this one we're gonna space partition. Um,
Getting
right, so we're
fancy.
gonna run create hypertable and add dimension. And so now let's take a look at what happens here. So I'm going to basically do the same thing that I did before, and you'll note then a few different things. One, so I should have some chunks now because I just inserted data. Um, and I do in fact have a chunk with that hypertable. And you'll see that it has the same thing. It also, though, like this is telling me something about the time that the chunk is taking up, but not anything about the space partition that is taking up. But if I look in dimension slices, you'll note, or I guess I should look at dimensions first so that you can see it, right? So I need to look in dimension. You see that we have two dimensions for this. One is my time dimension, which I had for all of my other hypertables that I've created, and the other is this this space dimension, right? And that space dimension is on symbol. It's a text, and you'll see that it has a partitioning function, which is get partition hash, and we also have a number of slices that's associated with it. It's also not aligned. So what does that mean? So we said that the time dimension is aligned, the space dimension is unaligned. We could also say this is an open versus a closed dimension. You'll note that one of the main differences between these types of dimension is how we're specifying how big the chunk should be, like how big a slice should be. So for one, we say we want it to cover 7 days worth of time. The other one, we say we want 3 of them. So for our time dimension, that's the open dimension. We say we want to cover this amount of time. For the other one, we say we want n of them.
So I have a question, and maybe this is jumping the gun a little bit, but so like the number of slices, the way that we're partitioning the space column, is there a way to specify that? So like say that you wanted more ways of splitting the data rather than just like 3 ways of splitting the data?
Yeah, you can when you add the partition, right, add dimension, we say how many.
Oh, I see. Okay, got it.
Right. So we say 3. We can also change our chunk time interval. We can also change the number of partitions, right? So we'll do that. We can do that later. So
do we have a default value for what we do for the space partitioning?
No, you have to specify.
You have to specify. Okay.
Yeah. And in general, right, this is mostly useful for multi-node where we're splitting this between machines. So that's like the main reason that you'd be doing this splitting is to scale out that way. So as I look at this though, so like let's look at this chunk. So let's actually look at the definition of this chunk. So okay, so we have 2 check constraints, right? So we check that time is between March 31st and April 7th, just like we did before. And we're checking that the hash of this symbol is less than some value. Right? And if we look at our dimension slices, you'll see that this range start to range end is actually going from the lowest possible integer, big integer, up to this value. Now, technically, I think our hash function divides the integer space. So now if I insert another one, if I insert some more data, I'll switch back to my other things to insert some data. So now we get apple. We want to create a different partition. We're going to insert apple. Right, and there you'll see that now I have another dimension slice. I have a different chunk that was created. Right, and now both of these chunks have the same range start and range end in time. But they have a different range start and range end in space. So if I were to look at an 01, right, I can see that now that's taking get partition hash of symbol and saying it has to be greater than or equal to this other thing. So that's the other side of the range. And if I look at my dimension slice information, right, it's going from this value to this, like, so there's another chunk that I could create that's somewhere in between those. And it looks like that they're like, once I create, so if I were to create then all of the chunks for this time range, or okay, so sure. If I were to create all of the chunks for this time range by, say, just taking this insert statement, we're going to copy it, we're going to paste it, and we are going to remove any symbol things. Or actually, we'll say and symbol does not equal apple, so we don't end up with duplicate data.
Should you also say CVS as well?
Yeah.
Oh, okay.
So we'll just say symbol not in.
Yeah, I was actually curious what those ranges would be if you included all of the data. So
yeah. And so we don't, again, we are not creating those ranges dynamically based on the data that we see. We are just dividing the space evenly into 3 parts based on what we know about our partitioning function. And I don't remember exactly, like, I think there's some ways, there's some hooks where you can set your own for that too. But I think that we only allow a small int number of partitions. So we maybe, I don't remember exactly how we're splitting it. But once we've done that and we've inserted everything else, you'll see that, okay, so now we have 3 chunks with stocks real-time SP, right? And they have the same start and end times. And if I look at my dimension slice thing, you'll see that I have another dimension slice, right, that is going from, like, in the middle here. Now, okay, so let's do a couple more things. One is I'm going to set my chunk time interval to 1 day. We already noticed what's going on there. And so let's just go straight to the next chunk or set of chunks. So we can just skip straight. We know that the end of it is April 7th, so we can just skip straight to that. We're going to insert one for CVS there. And if I look at this, notice what happened. I have another dimension slice in my dimension 17. Dimension 17 is my time dimension. Right? It's my time dimension for that table, dimension 17 here. But I do not have anything for dimension 18. I don't have anything new for dimension 18. Let's look at chunk constraint. Oh, darn it. No, I need... So you'll note that each of these chunk IDs in my new hypertable has 2 constraints on it. One in time and one in space. And that this one is repeated with a different space one. And that this one is also repeated. So the time constraint is actually repeated for each of these. Right? Those were our first 3 chunks that were created, and they have the same time constraint. It refers back to this dimension slice, right, over here.
So really you could think of the dimension slice information more so as like defining the constraints.
The dimension slices define our constraints, right? They absolutely do. And the but the point is that we're holding them constant if we can. So we're lazy about creating new constraints.
Right. Especially, I mean, if you already have a constraint that specifies the interval that you need, like, yeah, why create another one for
Exactly.
Like no reason. Yeah. Makes
Exactly. So
sense.
and that also limits the number of things that we need to search. So if you think about a two-dimensional space that we're searching, we search in just those two dimensions, and there are things ideally that are aligned along those dimensions, at least in some cases. And some are going to always be aligned and others aren't always going to be aligned. So one thing to note here is that if I so I could fill up this and we would see that there would be only 3 dimensions. But if I were to set the number of partitions before I do that, let's move this up. Right? If I set the number of partitions to 10 now, we set the number of partitions. Took longer than I would have expected, but whatever. So our dimension table has updated. Now we have num slices is 10. And if we look at chunk constraint, nothing has changed. We haven't inserted any more data. If I insert data now, so let's say I do apple now. This one. Okay, so I've inserted apple. I'm going to have another thing. Dimension slice. Now you'll note now, and with my constraints also, like if I had kept the dimension slices the same, I would have just reused the constraints. But here I needed actually a new one. I guess I should have done at least one more because then I could have shown you exactly what was going on there. But right, it reused the time constraint again, but it had to generate a new space constraint. Unlike last time where it reused the time constraint, or it made a new time constraint because that was the first one, but it reused a space constraint because they were the same number of chunks. Does this making any sense, Miranda? I don't know if I'm completely losing you.
So what I'm getting here is that if you were to change the space like partitioning from 3 to 10, which is what we did, and this is already on a table that has information in it, then when we'll only get a new partition. Well, when we add data, we'll get a new like space partitioning interval or constraint for like that newly added data, which is in our dimension slice table. Now,
and in
I
fact,
do.
if I do this here, right? So I've just done where I'm going to add everything else in. So we should see a lot more new chunks.
So what happens to the like old, because like the old space chunks are still there.
Yeah. So this is the fun bit.
Ahead. Okay.
This is the fun bit. Okay. So this is what happens. Oh. Really? Did it keep it the same somehow? Or am I just behind? That is confusing. What? Oh, that's why. Oops. I forgot to change my dates.
Okay, I was gonna ask. I was like, even for the same dates, it will not like, or we're expecting it to change. Okay,
sorry.
got it.
Sorry.
No.
Okay, so now we've done that. Hey, much better. Okay, so we now have a lot more chunks, right? But we don't have 10. Why? Well, I took over a third of the space when I made my first chunk, and I was still at partitions 3, then it repartitions the rest of the space, and it has some very actually complicated math to make sure that everything aligns properly when it does this, so that our slices actually are still non-overlapping and like covering everything. But I'm not going to repartition. So the one that I already did is not overlapping. It's not going to repartition. But the new stuff like works right. And the math there is a little bit hard. It's like a little bit weird. You have to make sure that everything works right so that you end up with with the right number of chunks, and you don't end up with any data that has nowhere to go. That's a really important thing, right? So there's all of these weird bugs. I think Matt Fay actually wrote a lot of that back a long time ago. So this is a lot of the early inner workings of Timescale on this chunk and partitioning behavior. It allows us to look this stuff up pretty quickly, which is really nice.
So
But you'll notice that here it did change. And this is when we went back and we looked at the dimensions and we said, hey, so this dimension is aligned and this dimension is not aligned. Right. So we said that the space partition dimension is not aligned and the time dimension is aligned. So what that really is telling us is if we look at like, okay, we're creating chunks, right? So, and I can do something like this where I start off with 1 chunk and I'm going to 3 chunks. Right, and that happens over time. Or if I'm going from and time is going this way in this case. So if I'm going forward in time and like I insert first here and then the other ones get created, like these chunks are sort of possibly there, but not there yet. When I change my amount of time, it's always going to remain the same across the time dimension. So those have to be aligned. But I also changed the space, and that isn't aligned, but it's going to align over here with this next one, maybe. Right? So some of it will be aligned and some of it will be unaligned. And that's the difference between the space dimension, is where we don't always force it to be aligned in that dimension. And I think we're over time now, but if anyone has questions, I don't know if this was useful for folks. I hope it was. I think that there's a lot of interesting stuff here that might actually be helpful for folks. Miranda, I think you had a question though.
I did. Yes.
Okay, let's
If you
go
go
back.
back to the code.
Yeah.
Okay, so just to I could have missed something. So
Yeah.
that's my bad if I just miss us.
It's
But
totally
okay.
fine. I feel like I'm not being horribly clear with this. It's like it's a little bit of a complex topic. Anyway, yes.
So my question is, so we have following the dimension ID. So like 18, we create for dimension ID 18, the first one, we're creating but higher up. So the 318s before that. So are those just okay? So like that first one,
that was because at first we had 3.
Right. Yeah. But my question, I guess my question, if you go back to so like we created 3 chunks that covered the entire interval from like, -9 blah, blah, to like, yeah. So we covered the full range and then we changed it to 10.
Yep.
So why is it that
we changed it to 10 after we'd already inserted some data in this next thing?
So is it because the next insertion of data was a different time period? Is that why we're still seeing those old 3 partitionings?
It's because it was the next time period, so we created a new chunk in the next time period that covered some amount of space. So we covered essentially like when we first inserted, we were over here, and maybe we let me see if I can actually like draw this for you. So we'll duplicate this. So we were here, and we'd already inserted into like 2 chunks, and then maybe we changed our dimensioning. So then once we inserted this stuff, it got something like this. And then in future chunks, it's going to be all 5 at the right edges. So if I were to, maybe the simpler way to put this is if I were to change this again and insert into another time period, let's see what happens. So let me, instead of setting this to 10, let's set this to 12. No, let's go down a little bit. Let's go 5. So we're going to set that to 5. And then I'm going to go to the next day and I'm going to do all of the stuff.
And so, okay, my assumption is that if you use a new time period that we have not inserted any data for into this table yet, that it will like evenly split the 5 partitionings. Is that correct?
Yes. So we will get, we should get, I think at this, so we right now have 1, 2, 3, 4, 5, 6. Let's just do a where clause. Select. Right. So before we do anything more, like we have 10 dimensions for dimension ID 18. And when I insert some data here, right, if I insert all of my data so that I should hit all of my partitions, I've now reduced my number of dimensions to 5. I should get now 5 new things, because unless one happened to be the exact right size, which I doubt it was. Let me just see. We've inserted the data. It's in a new time period, right? And if I do that again, haha, we have 15.
Okay. So really,
so it's now.
Yeah. So just tell me or correct me if I'm wrong, but my understanding of this is that if the space, if you insert or like change something with the space dimension, that if you already have data in the table pertaining to that space, it will not like add or change any chunks like that were.
It won't change any chunks that were already created.
Right.
If there's some chunks that haven't been created yet, it will use the new thing and figure out where to cut them.
Got it.
So that the other chunk doesn't have to change.
To the best of its ability, kind of like
yes,
adjust things. But then like any new time periods that you add data for, and if there's not a space partition that already kind of has the constraints that it needs, then it will like correctly like create those new constraints.
Exactly. And so it's trying as hard as it can to figure out how to divide this stuff evenly and all of that stuff. But it's not always easy to do that and do that correctly. And so there's a lot of weird edge cases that we just have to deal with. Is really like, again, you don't have to deal with this as the Hypertable user. You just like do the thing and it basically just works. The one thing is that because time is an aligned dimension for various reasons, we say like, look, you do have to wait until that time period passes, and then the chunks created after that,
you'll have kind of the rules.
We'll have but for everything else, right, we try to do what you want as soon as possible and give you more, at least more dimensions, even if one was already created. Like maybe we can do the rest of them into like as if there had been 10, but we'll cut it at the right place, right? So it's sort of aligned-ish, but not quite. And we're always dealing with these ranges. So we're dividing the hash space into some number of dimensions. Now, and so that's one of the things that, you know, you could play around with if you wanted to try to get something like 1 dimension per ID. You would have to use a small int, because I think that's what we use for the number of dimensions, and you'd have to, and you could like then pass it a small int and say, I want the maximum number, like the max size of a small int, dimensions or partitions. What do we actually call it? Whatever, doesn't matter. Yeah, set number of partitions. Anyway, so that's like one weird hack that you could do if you really wanted that. I don't think I recommend it, but it's a thing that you could do in theory, at least. And you'd have to have no, anyway, there's all sorts of things that you could think about there, but that's one thing that you could potentially do. And so that's a thing that I would just like, that's a cool thing that you could try and could be interesting for you. So or like that's another thing that you could take a look at. Like, but just understanding that this is always like we're trying to create the smallest number of dimensions we can, where it's allowing us to search better for where we need to look, right? So when we are doing inserts, we can figure out which chunk we need to direct things to very quickly with this. It allows us to work very nicely with indexes, with B trees on these range start and range end columns, so that we can locate the chunk that we need to insert into very quickly, even if you have a fair number of chunks. It means that we're not storing extra information. We don't actually need to look at each chunk individually to be able to say that like we don't need to look at the constraints on each individual chunk to be able to say that it is not valid for this. We can instead just look at the dimension slices that we have, right? So there might be 3 or 10 chunks in the same time dimension slice, but I don't have that time dimension slice repeated 10 times. And I have to identify all of those. I just have to identify one, and then I can figure out which chunks have that. So it's actually much more sparse, or it's much more space efficient in terms of looking up what we need, so that we don't need to go and look at each chunk individually. We can just look at the dimension slices, which often are like, you're usually in the real world, you're going to set the number of partitions if you have a space dimension, and it's going to stay that way for a while. There's going to be a lot of time chunks in between that time and the next time that you go up to another larger number of space partitions. So those are going to be aligned, and we're just going to reuse those same constraints. And there's only going to be one entry for that in the dimension slice table. So even if I have 1,000 chunks, each with the same space partition, they'll each have the same space partition constraint, and I can look up that dimension slice. There's going to be one entry for it. I don't need to look at all 1,000 chunks. I look up one entry for the space constraint, one entry for the in the time dimension, and boom, I've got the chunk that I need to go to. I don't need to look at all 1,000 chunks. So that's one of the key things that really helps us improve the performance here, is that we're not going through all of the individual things to try and figure out where we need to be located. So it also makes enforcing that these things are non-overlapping, right? Which we discussed some of the indexing stuff and how unique indexes rely on the fact that chunks are non-overlapping along those dimensions. So it makes enforcing that very clear, right? Along a dimension, we can't ever overlap. We have these ranges that we have to adhere to. It means you also like can't change your partitioning, like your hash function part of the way through, because that would cause weird shit to happen. So at least if you have a unique index. But it also, yeah, I mean, it very much means that you can't do that, because all of the old data in that space partition would now be like invalid. And we don't have a way right now of saying, hey, on the next thing, change the partitioning function to this. So if you need to change your partitioning function ever, that's a new Hypertable type of thing. So that's just like some of the stuff that like some of the like I said, these are implementation details. These are not things that you need to know in order to work with Timescale at all. They're very useful, and part of the reason we're doing this, right, is for our folks. Like if you're working on Timescale, if you're thinking about contributing to Timescale, right, this might be useful information for you. There are some optimizations that it might also help. So.
Yeah, that's what I was thinking of, is like, I feel like this information is really helpful, like for me, in thinking about how, like, something that I can consider now when helping a customer,
Yeah.
or a user that's like having performance issues, and thinking about like, oh, is it possible that they could have, started with a ton of chunks that they don't need, or like a really large chunk and then switched it, but like didn't, we're not at the time point now where it's like,
right,
this new
exactly.
partitioning will actually kick in.
Yeah. So it's really helpful, I think, for your mental model of what's going on under the hood.
Yeah,
It's
for sure.
not, and so there are specific situations where it might be helpful for improving performance and doing other sorts of stuff. But it's really more about like, okay, I have a bit more of a concept of what's going on here. I'm not going to use this every day. I might use it a little bit when I'm setting up if I really need to tune something or whatever else. But it's much more just like, okay, I have an idea of what's going on and how this is happening in the background. So a lot of what Timescale is doing is making that partition creation. It's automating that completely. It's doing it in real time when you insert data. We're not waiting. You don't have to run a job in the background, and if it fails, then your data has nowhere to go. You're not ending up with data in a weird place. We're always making sure that it has a place to go, that it's going to be separated correctly according to the things that you want it to do. And it turns it into this operation that happens at insert time, right? During DML, data modification, rather than DDL at like chunk creation time, which also means we have to worry about locking and other sorts of stuff and making sure that all of that works correctly. So you're not taking overly harsh locks on the table and blah, 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 blah. So that's how we manage a lot of it. And hopefully that's useful for folks. So that's that. Hopefully that was useful. Please do provide feedback. Let us know what you like and didn't like in the comments. I also will say that I think next time I'm going to be on vacation, or I may be here for the public one. For the private one, we're going to have someone else doing it. I think actually 𝗙𝗂𝗋 will be doing a presentation, and I'm going to get to be like, both Miranda and I can be in the Miranda role of asking 𝗙𝗂𝗋 annoying questions. Not annoying, not actually annoying at all. I love your questions. They're never annoying, truly. But when I'm doing it, I will be annoying. So that's my goal, really, is I'm gonna ask so many questions. Just like you all, it should be your goal to ask so many questions that I actually get annoyed. If you can manage that, I will be very impressed. But yes,
send you like a hat or something.
So one of our colleagues, 𝗙𝗂𝗋 Steenbergen, will be doing a lesson on explain, which is a really great Postgres feature, if you don't know about it, that tells you how queries are actually being run under the hood, and tells you a little bit about what's going on there. So that's going to be what he's going to talk about, and I'm very excited to see that and get to ask him questions here. So woohoo! Thanks everyone, and we'll see you in a few weeks.
Yeah, thanks for hanging out with us. It's always a pleasure. See you next time.
Bye.